In the previous video, we introduced self-inductance and looked at the electronic device called an inductor. Now I'm interested in seeing what will happen if we put this, combine this with other electric circuit elements. So let's start by taking a look at an energizing, is how it's often phrased. Energizing RL circuit. So here we will have in series an EMF source. We'll go ahead and throw in a switch just so we can, which we will close at time 0. We'll put a resistor in series and an inductor in series with that. Now, when we close the switch, we're going to go ahead and get a current going around the circuit like so, and it will be clockwise because this is the positive terminal of the battery. And so we can start to analyze the circuit using Kirchhoff's loop law. So if I start in the lower left-hand corner and start walking my imaginary dog clockwise around the circuit, I exit the battery at the positive terminal, so I'll write plus the battery EMF. Go through the resistor in the direction of the assigned current, so that's minus IR. And then we saw that this would be minus L di dt in order to generate a back EMF. And then I walk my imaginary dog back home and write equals 0. So we can go ahead and work a little bit to put this into standard form. So first, let's just rearrange L di dt plus IR equals the EMF, then di dt plus R over L times I equals the EMF over L. And we've seen an equation that looked like this before. It was when we had a charging capacitor. So instead of an inductor in the circuit, we had a capacitor in the circuit. And instead of the current, we had Q for the charge. Where we had R over L here, we had RC in front of the charge. And we identified that that was the time constant. Since this has the exact same mathematical form, we're going to get the exact same mathematical relationship. So we will identify this as the time constant in the circuit. And since we solved this the exact same way that we solved it for the case of the charging capacitor, and it was a tedious solution, I'll just save you the grinding of it to get that the current will be equal to the EMF over R. Because remember, after a long time, an inductor will act like a wire. So this will be our final max current times 1 minus e to the minus t over, minus t over tau, where tau is equal to L, sorry, that's 1, oh, I meant to say 1 over tau before, my bad. 1 over tau. So where tau is L over R, which is again a time constant. And yes, 1 Henry per ohm does indeed equal 1 second. I encourage you to try that out for yourself. So we'll see the exact same behavior we saw before. So if we plot the current through the circuit as a function of time, we're going to see that it ramps up asymptotically to E over R, and when you get to about 63%-ish is when you will have passed 1 time constant. Okay. So now let's go ahead and take a look at the case where the inductor is de-energizing. So here, in order to de-energize it, we've got to be a lot more careful than the way we did this when we wired up a similar circuit for capacitors. And you'll notice here I am drawing a very different symbol for a switch. More on that in a second. There. So, and then here I'm going to just go and hook that. Oops. I'll just go ahead and hook that into the circuit right there. Okay. So what's up with this really weird switch symbol right here? This switch symbol is for what is called a make before break switch. Most switches that you run across are what are called break before make. So for instance, if you think about like the Frankenstein style knife switch, you disconnect it from the one place, breaking that connection. You swing it over and then you make the other connection. So there's a period of time where nothing's connected. With this circuit, it is vitally important, as in lives could be at stake, that you use what's called a make before break switch. In a make before break switch, it's exactly what the name implies. When we go ahead and throw this switch at time 0 to the other position, we need to first make this connection here before we break that connection there. So I want you to think about why that would be so important that we do that in this case. Pause the video, come up with your thoughts on that, and then get back with me. Alrighty, so the deal is that if you were to, remember, an inductor is always striving to keep the current through it a constant. So while when we had the switch in this position here, this was for when we were energizing the circuit here and we were running a current around like this. Now, this means that the inductor is going to see a downward pointing current, and then no matter what happens, it's going to endeavor to keep that current a constant. So if you were to have a break before make switch, there would be no physical connection here, but the inductor is going to do everything it can to keep the current through it a constant. That means you're going to generate some really big potentials because, after all, if you had a current and now you don't, d-I-dt is basically infinity. So that back EMF is going to be really, really huge. Voltage is so high that you will easily complete the circuit by jumping a spark within the switch. Now, sometimes it is the unfortunate case that if you're to use a break before make switch, part of the way that that circuit will get connected through, if you have completely broken both connections, is that the spark will jump through the person who threw the switch. And this can be deadly, depending on the size of the inductor involved. So this is something you very much do not want to have happen. So whenever you're designing a circuit like this, you absolutely have to use a make before break switch so that there is always a connection to something so that you don't jump that spark. All right, so now let's go take a look at how the current will be continuing to flow after we have thrown the switch. So after we've thrown the switch, the inductor is still going to be trying to keep the current going through it. But now this is our new pathway here, like so, because we've taken the battery out of the circuit when we threw the switch. So we can still go ahead and do Kirchhoff's loop law on this. So we can imagine walking my imaginary dog clockwise around the circuit. So we go along. The first thing we hit is going to be the resistor going in the direction of the assigned current. And then we'll be going through the inductor in the direction of the assigned current. So it'll be minus L di dt. And then that will be equals 0. So we can go ahead and do the same kind of deal here. We can rearrange, well, we can just multiply this through by -1 to make the minus sign go away. And we recognize that we've got the same kind of deal that we saw with a discharging capacitor, except that instead of a charge now, it's a current. And so again, I'll spare you the derivation, but the current will be at all times will be equal to the current at time 0 times e to the minus t over tau, where tau is our time constant, L over R. There. So let's go ahead and, so again, we can go ahead and plot this. And I can plot the current. So this will be I naught. This will be time. And remember, the magic number is 37%. After one time, oops, let's draw it a little more better, about there. So after one time constant, we have dropped to 37% of our initial current. And we'll just asymptotically drop off to 0. So you might use this for, say, some kind of circuit where you want to do something initially and then fade away. Although sometimes you use this actually just plain to store energy and then deliver it in a hurry. Like, for instance, running the spark plug in a internal combustion engine. All right. So with that, let's go back and revisit what we had right here. So let me just, so we can have a point of discussion here, let me just go ahead and copy the picture. And put it here, and then we will also go ahead and copy out our Kirchhoff loop rule here that we had before, and put it here. All right, so this time I'm going to rearrange it to put the EMF to the left and the other terms to the right. So this will give me the EMF is equal to IR plus L di dt. Now, if I were to multiply everything through by the current, this term here on the left will be IE. oops, be IE, and this will be I squared R. Then we have a plus LI di dt. Now we've seen the first two terms before. The first term, the IE, this is going to be the power delivered by the battery. The I squared R is going to be the power dissipated by the resistor. So then that leads to the question of how do we interpret this? It definitely has the units of watts, so, or joules per second, but what kind of physical interpretation can we give to that term? Go ahead and pause the video and see what you can come up with for that. Okay, well, we know that energy has to be conserved at every instant. So here, this is the number of joules per second that's being delivered by the battery, and this is the number of joules per second that's being radiated off as heat in the resistor. Now, we know that these two aren't going to be equal. The power dissipated by the resistor will be less than the power delivered by the battery as the current ramps up. Eventually, asymptotically, this mystery term will go away and these will be equal. But during the energizing process here, the resistor will be dissipating less heat, heat at a slower rate than work is being done on the circuit by the battery. So the energy has to go somewhere, and the somewhere is here, and this has to do with the inductor. So we can conclude that this has to be the rate at which we are storing energy in the magnetic field of the inductor. So it's taking work to build the magnetic field in the inductor. And so, for instance, here, when we closed the switch here, because we had this magnetic field, as the magnetic field started collapsing, that was a time-varying magnetic field, which we have seen by Faraday's law, will induce an EMF in the coil to keep things going. So it takes work to build the magnetic field, and then we can get that energy back out when the magnetic field collapses. So we will identify this as the rate at which energy is being stored in the magnetic field, and we will just call this, we'll just go ahead and call this du sub b dt. All right. So since we were able to identify that this term means that it's the rate at which we are storing energy in the magnetic field, in other words, the work being done to build the magnetic field, we can actually come up with an expression for the potential energy, the magnetic potential energy in the inductor. So we can do dUB dt is equal to Li di dt, and then we can re-express this as differentials to say that this implies that du by itself must be equal to Li di. And then we can just go ahead and integrate this out. This is going to be equal, we'll integrate this from 0 to our final potential energy. We start with a current of 0 and we integrate up to I. And so this will give us that the magnetic potential energy is equal to 1/2 Li squared. And just for comparison's sake, we remember that in a capacitor, the energy stored in the electric field was equal to Q squared over 2C. And we're going to follow the same kind of trick here. Remember, we found the energy density, the electric potential energy density stored in a capacitor by taking a parallel plate capacitor and dividing by the volume between the plates. We're going to do the same thing here except for a solenoid. So we'll just go ahead and imagine figuring this out for the case of our inductor being a solenoid. And we remember that we got that the inductance for a solenoid is equal to mu naught n squared over L times the cross-sectional area of our solenoid. So we can say that the energy density, which is the energy over the volume, this would be the magnetic potential energy, and the volume would be the length of the solenoid times the cross-sectional area. So we can go ahead and put in that this is 1/2 Li squared over AL like that. And then we can substitute in our expression for L. So we have that UB is 1/2 mu naught n squared over LA. And this is going to be over A times L. Cancel and cancel. And we are, oops, and I forgot my I squared, my bad. So we have that this is, clean this up a bit, mu naught n squared I squared over 2 L squared. Alrighty, but you'll also remember that we found that for a solenoid, the magnetic field strength was mu naught n over L times I. Well, here I've got an n squared, an I squared, and an L squared, so that would be like a B squared, except I've only got 1 power of mu naught. So that means that all this stuff here, except for the 2 and the mu, except for the 2, is B over mu naught. So making that observation, we get that our energy density is 1/2 B squared over mu naught. And again, for point of comparison, remember that we saw for the electric field, the energy density was 1/2 epsilon naught E squared. And again, like when we did this for the electric field, I'm going to go ahead and assert that even though I only did this for the case of the magnetic field inside an ideal solenoid, the result is true in general. All right, so in the next video, we will go ahead and take a look at LC circuits and see how we can use those to make a radio receiver. Catch you over there.